Okay, welcome back. Welcome back. We will continue with our discussion on the perceptron idea. I want us to go through the details of how the optimal solution is computed in the perceptron, because later on, all we need to do is just change the threshold. I mean, not threshold, but the activation function, the sigmoid function, from just linear summation into something else. Then we will be able to see to compute the optimal value of the weights using exactly the same method. The only difference is the activation function. Okay, so now let me. Okay, so let's go back here. So this was our function O, given inputs W x0 is 1, so W x0, W1 x1 up to Wn xn. So it is just a summation of inputs multiplied by the weights. So our problem here is to know what are the proper weights so that we can classify properly the output given the inputs given the corresponding inputs. Okay, so now how do we learn the W's? So let's first consider the error. So the target value minus the computed value from here. So now the target value is given from the table, where your D or I, you can call it I. For the most part, we call it I, but here D. So your D or the I data or the ith row in terms of the full data. The big D is we can say that the big D is the table. Okay, and the small d is the row. Okay. Okay. Now again, we take the square of the error. There's reason for that, so that when we take the derivative of this, the 1/2 will go away. Okay. So now, okay, sorry, the 1/2 here is there's a reason for the 1/2, so that when you take the derivative, this one will go away. Okay. The square is to make sure that the sum, the reason for the square is not that one. The reason for the square is to make sure that the errors are the absolute values, and that so that the error terms won't cancel each other. Okay. So we take the square root of the error terms. I mean, the square of the error terms to keep them positive. Okay. So the gradient of the error, the partial of E with respect to W0, partial of E with respect to W1. So if you can see here that E is like that, 1/2 of T minus D. So we have error is equal to 1/2 of, okay, T, we'll just write it T1 minus output 1, like that, squared, because it is a summation, plus T2 minus 0.2 squared, plus T3 minus 0.3 squared, and so on. Okay, up to n. Tn minus output n. Okay, so now how do you take the derivative of this? So we say that, okay, here with respect to W, but where is the W there? Where is the W here? What is the partial of, let's just say here, partial of E with respect to W0? Where? Well, we take the partial of this one with respect to W0. That's it. How? Well, these are outputs, right? Okay. Outputs with respect to, okay. So now, what is O1, O2, and O3? Okay, based on the input X, right? So O is based on, okay, the weights will become the same, W0 times 1, X0, plus W1, X1, plus W2, X2, dot. Okay? So now with respect to W0, so this one is depending on the input X. So, and then the output T1, the input of the first set of input X1 up to Xn, the second set of inputs X1 up to Xn. Okay. I wish I have a table to, because that is important. Okay, wait, let me have a table. I want to show a table of data. Okay, so let's have this. We are looking at this one. Okay, now I will put it here. I want to give a table of data for us to consider. Okay, let me delete this one. Okay, so now, so we are given the ith term, for example. Okay. So let's say, for example, we are doing experiment. Okay. And let's say, for example, that this experiment gives us inputs of maybe X1 is the temperature, maybe. Then X2 is the, let's say, wind speed. Okay. And then probably X3 is lighting, okay, sunlight. Okay, and what else? Well, I'm talking about you're putting your laundry outside of your house. So these are the parameters that can affect how your laundry will become dry. Yeah, at a given time. So temperature, wind, sun, and what else? Okay, maybe the neighbor's dog. Yeah, if the neighbor's dog will come and try to move your laundry, so it will become faster also to some disturbance. I mean, disturbance will make your laundry faster to be dry. So this is the output. The output is, say, the dryness of your given this one, and this is the dryness. So now this is the first instance that you do the experiment. So there will be 0.1 temperature, maybe 10 degrees, or how much? Maybe 20. Now there's no 10 degrees here. It's like, let's say 35 degrees centigrade. Okay, that's around the time, the temperature now. And then the wind speed is how much? Let's say 1 meter per second wind speed. Okay, meter per second. And then the sun, in terms of what's the unit for sun? Luminance or lumens, yeah. So maybe 5, let's say 5, I don't know, I'm not sure if it's lumens or what. So let's say that's correct, 5 lumens. And the dog, presence of the dog, maybe he was there for he do your laundry for around three seconds, move it around for 3 seconds. Then now okay, after some time, the temperature, I mean, the laundry is dry by around 40%. Okay. Okay. Now the same another experiment. Okay, like that. Okay. So temperature is 37. Okay, wind speed is 0.75, or let's say 0.8, so it's fast. Then lumens is 5.2. And dog disturbance is around 4 seconds. Okay. Then maybe this one is faster. So this is 0.5, 50% of, okay, let's stop there. Anyway, so there, that's your data. And then we can have several. Okay, so you take all these inputs and then this is the output that is based on the data. The same thing here. So now if you compute your output, okay, so you compute your output, okay, based on the weights. Okay, again, this is the same thing as the polynomial that we discussed, based on the weights input plus W1 X1. So what is your X1 plus W2 X2, W2 X2 plus W3 X3. I should have done at X3 plus W4 X4. Okay, because we don't know what is the weights that will, so for each of these X's, for each of these, you will have to input them here, yeah? And then we don't know what is the correct value of the weight, so we randomly put value of weight. So that's what, then here, you will compute with some output, okay? But this output definitely will not be the same as this, okay? So the idea is to look for the W that will lead us to the close output according to our experiment, okay? So now, but then we want to take the partial of the error with respect to the weights W. So where is it here? So in this case here, we have 1/2. Okay, when we take the partial of this, well, we can take the summation. So we can remove this and then take now multiplied by, so each of these will be multiplied by 2. Each term multiplied by 2 times T1, okay, minus 0.1, okay, and then the derivative of this one. So what is the derivative of this one? So the derivative of that T1 is 0, the minus what is 0.1? This is the 1, okay, based on the first input. So with respect to W0, okay, so we take partial of E with respect to W0. Well, you take, that means that you take the derivative of this with respect to W0. The rest of them are not with respect to W0, and so this is just 1. The rest of them are 0, right? That's a 1. Okay, then plus, okay, the same thing, 2 times T2 minus 0. Okay. We are talking about with respect to W0. Okay. So W0, and then here, again, you have this one as well, the same thing. It's a 1, and so on. Okay, and so on. Okay. And so this one will be just 1. So remove the 2. So it will be just the same thing, the summation of EI minus OI, that's it, times 1. Okay, that's the gradient. Okay, partial of E with respect, I mean the first part of the gradient. Now we do the same thing, partial of E with respect to W1. So partial of E with respect to W1, I think it's there in the subsequent slides, but I want to do it here so that we can see. So again, this is 1/2, and then multiplied by twice, and then that term T1 minus O1 multiplied by, now this is the what. So now we forget about this, that we take the weights here. Okay, so now it is W, we take the derivative with respect to W1, and so what's remaining is X1, right? X1. Sorry, this is W, this is W1. W1, and so that's X1. Okay, and so on, plus 2, and then T2 minus O2. Okay, the derivative of O2, okay, with respect to W1. So again, that is X1, and so on. Okay, so that means this is equal to the summation of Ti minus OI multiplied by what? X1 all the time. Okay, so remember, this is partial of E with respect to W0. And this one is partial of E with respect to W1. So now you can see the pattern. So that means that the partial of E with respect to Wi, okay, this part here will be equal to minus N times what? This one. Summation of Ti minus OI multiplied by Xi. Any questions?
So I don't understand why it's called the partial of E to W0 when there's no W0 in the formula. It's just T's and O's.
T's and O's. Okay, the O is this one. It has W. It's a function of W. The O is that output, the output function. I understand it's a little bit confusing because of the way they assign the names. But yes, the O, the T is this part here that's computed from the table. The O is what we the T is what is given by the table. The O is computed by this equation as a function, as a linear summation of the weights times the inputs. So the W0 here multiplied by 1. That's why here. So yeah, so we take the derivative of that. So we just write this one. We take the derivative. So we take the 2 here multiplied by this original term multiplied by the derivative of what's inside. So there's no zero derivative on this one. So we take the derivative of this O1. So we take the derivative of, with respect to W0. So this O1 with respect to W0, this one. Partial of O with respect to W0. So this becomes, this one does not, are not with respect to W0. So this is 0. So now this is 1. And so that's 1. So that's minus 1. Because there's a negative sign there. Okay? Okay, there's a minus 1 here. It should be a minus 1. Okay? And then here again, this is okay. There should be a minus here. Minus X1. So there should be a minus X1. So there's a minus X1. Yes. Okay. Okay. So I don't want to remove this data because I spent a lot of time to, I just erase it from here. All right. So it's a big word. Never mind. Okay, I want to keep that table. That's why I want to just keep this one. I could have took a picture of that so that I can just open it. But anyway, it's fine. I changed my mind. Okay, before I do that, I take a picture first. Print screen. Okay, that's our data. So let's clear everything. So now I can go to the next slide. Okay, here. So now, so that is the case. So partial of V, oh, I have shown this to you already. So partial of, okay, you take the partial of V with respect to WI. So partial, the E is that part. Okay, there. It's already shown here. Okay. This is the E part. Okay. Okay, now we take the partial of this with respect to WI. So now this one, you go inside because this is summation, and so that's fine. You go inside. So now you take the derivative of this. Once you take the derivative, you bring the 2 here, so the 2, and then derivative with respect to WI. So put the 2 here, write this one, and then derivative of this inside with respect to WI. So now that is that part. Derivative of the inside term with respect to WI. But because this is a constant, so there's no derivative. So here the output D, you just multiply this one with that function summation W dot of X dot. So this is equivalent to W1 X1. Okay, sorry. W0 X0. This is equivalent to W0 X0 plus W1 X1 plus W2 X2 and so on. You understand? W2 X2. Okay, you understand? Because this is just, well, if I write it out, this is the dot product of W1, so W0, W1, W2, up to Wn, multiplied by, that's why it's a dot product of X1, X2, and so on, Xn, okay, of the ith or the dth entry there. So that this one is the same as that, okay. The derivative of this one is 0, and so now we take the derivative of this. But we have shown it already that with respect to W1, so with respect to whatever W you are using, then you can have that Xi. So it was in our case X0 or X1 or X2. So depending on what your W that is considering, then that is the corresponding X. Okay, according to the data entry. Okay, that's why they use the Xi, because in that case, okay, in that case they use the small d, because in our case they use the Xi, so that it's easier for us. I mean, it's not confusing for the index. So the small d is the row of the table that we are looking at in terms of the data. Okay, the I corresponds to here. So I took a picture already. So the I corresponds to the ith W, okay? And then the D corresponds to the row. So here I should, instead of I here, it should be the D, the row of the data, okay? So this is the D. So your input here. So the Xi, so if with respect to X0, that's a 1. So that's 1 all the time. I mean, with respect to W0, this is a 1 all the time. But with respect to W1, then this is X1. X1 of the D data. So that means X1, that's a 35. Okay? So anyway, okay, I think that's understood. So we go on to the next. Okay. So the idea here is to, I will, you have this, you have these slides. We have the slides on the blackboard. You can look at it. anytime. So the idea here is you have this x. Okay, let's just put this d, a small d, because that is what they're using. So you have the x input as well as the t output, the scalar output at this time, and then you have x input that is a vector. And so now your learning rate can be assigned to 0.05. So that's the idea. You're given the input and the target value, and now we are going to look for the weights. The new weights that will update, okay, that will give us a new W that will be the optimal value for the weights, that will minimize the error term here, okay? So we have seen already that the gradient of that, okay, the gradient is the summation of this, summation of target minus output times multiplied by the E. And so the target minus output multiplied by the XI, okay? So now, so in summary, this is how we are going to input. Now the question is, why is the summation gone? We used to have summation here. Okay, there's the summation. Why in this case here? Why is this summation gone? We don't sum the targets anymore, multiplied by the XI. Remember here, you have any idea, Bright? Okay, it's here. I didn't show the entire. Why is the summation here gone? Is this a correct equation? We used to have summation here. There's summation. Why it's here, not there? Summation of TDOD minus XID. So now this is T minus O only. There's no summation. Why there's no summation? Right? Are you saying something? I mean, it's what your mouth is opening. Huh?
No, I'm not saying anything.
Okay, say something. Why do you think there's no more summation there?
I think this is for a specific.
Huh?
This is for a specific I. So
Okay. Yes.
so we don't need to sum all the T minus O's because this is only concerned with the specific I that we're dealing with.
Are you sure? But the whole thing is supposed to have, remember, in this case here, remember that the whole thing is supposed to have this one. You take the original function, this part, okay? So we update W in terms of, okay, in terms of delta W and then N T minus 0 XI. So this is the perceptron rule. okay? But then the delta W, it's supposed to be the gradient, okay? The gradient of E of the error with respect to W, okay? And in this case here, the gradient of error has that summation. So now here, it is gone. Why? Are they equivalent? Okay, let me
No,
write.
one is a
Summation.
delta, and one is just a derivative, so they're not equivalent.
You're not equivalent? Why is the summation gone? Is it, first of all, okay, if they're not equivalent, then there's something wrong with our derivation then. We didn't derive it correctly. Are they the same or not the same? Yeah. We take all the pains of deriving it, and now we arrive at this equation, partial of E with respect to the partial of WI. And now suddenly we are given this. Without the summation. Are they equivalent? Okay, I think let's wrap up this one. Okay, they are equivalent. Okay, why are they equivalent? Well, you take note of because here, okay, that is a bold T and a bold O. Okay, those are vectors. Okay, the result of this one is a vector. Okay, the gradient, this one, delta Wi is therefore delta of Wi, okay, 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 let me here is equal to, okay, now it looks like no, there should be okay, maybe there's some notation there that is not correct, but they are equivalent in the sense that, okay, let's just don't look at this one. They're equivalent in terms that this is a vector and that's a vector. Let me see if I can arrive at something. So now you have T1, okay, T2, the target value, that is this one, T3, okay. So T1 minus O1, okay, T2 minus O2, okay, like that. T3 minus O3 and so on until Tn, okay, the number of data, the data, On, okay, multiplied by another vector, okay, x. Remember this xi, it is with respect to the d, okay? So the d, the data there. So that means there's an xi according to first data. There's an xi according to the second data, okay? There's an xi according to the third data. What does it mean? Xi to the nth data. What does it mean? Okay, so the reason the summation is not here is because this, okay, I think this should be the other way around. This should be transpose, okay, so that now you multiply this with that one, that's the summation. So when you multiply this T1 O1 multiplied by X1, T2 O2 multiplied by, T1O1 multiplied by Xi1, T2O2 multiplied by Xi2, T3O3 multiplied by Xi3, then that's where the summation comes in. Okay, so this should be the transpose, so that this one will, this is the comma, this one will go straight like that, and then you can multiply them accordingly. So this is how the summation is done. So this is, okay, this is equivalent to this one, okay? So in the sense that here, what is your XID? Okay, so that means that in this case here, for example, if you take the derivative or the partial with respect to W1 only, so W1 only, you take all the Xi's here, the X1 with respect to the D data. So that means all this, all that information there is the one that you will put here. Okay, multiplied by the target, multiplied by the difference of the target minus the output. So that's the case. That's why here you just put Xi, okay, multiplied by T minus O. Okay, now this is the one that confuses me, the gradient of Wi. Okay. Now, is this, okay, is this a vector or now I understand. So here, this is gradient of Wi. This is not a vector. This is a scalar value. Okay, that's the one that confuses me. Yeah, this is scalar value because when you sum that one, it results into a scalar value. Okay, so this is scalar, but these are vectors. This is a vector, that's a vector. So for every delta of Wi, that means if you take this Wi of the first W, okay, well, you have W0, W1, W2, okay. So if we write it down, then we have W1, or let's just start with W0, W1, W2, and so on. Well, you have W4, 3 up to W4, because that's how there are only 4 inputs, okay, is updated from the initial value of the weights such that your delta W plus your delta W is this one, delta WI. So delta, let me write it down, delta W1, delta W2, delta W3, and delta W4, where you can get it from here. Okay, that is scalar. But then the summation is gone because these are vectors, and that's how we multiply them. Okay, you understand? Okay, any questions? Okay, so now that we learned the how we update the to search for the optimal value of weights for the perceptron training rule, then all we need to do is change the activation function. Then we can, if the activation function is changed, then we can now compute also the optimal value of the weights. But then the only difference will be how the gradient of W is computed. Okay, then if you're able to change this one, then that's it. That's the activation function that is used for the back propagation. So next meeting, we will discuss on how that one is computed. And then we will, I think we'll finish the computation for the optimal value of the weights, and then we can discuss one example. Okay, and then for the following meeting, we'll complete the example. Okay, let me stop sharing. Any questions? Okay, let me record. Let me stop recording because